Bismillahirrahmanirrahim. In the last video, we have discussed the basics of the induction motor, and we have derived the equivalent circuit of the induction motor that is shown in front of you. So, the equivalent circuit basically used to determine all the losses in different parts of your machines, in the stator, in the rotor, the magnetization losses. So, you can see an impedance over here, the stator impedance. Let me call it Z1, that is equal to R1 plus JX1. So R1 is the resistance of the copper winding of one particular phase. This is per phase equivalent circuit, and X1 is the leakage reactance of the stator side. Then coming towards the rotor one, JX2 and R2, this represents the rotor resistance. Let me call it Z2, R2 plus JX2 is equal to Z2, that is the impedance of the rotor side. And then we introduced a resistance in the last lecture, that is R2 into 1 minus S by S. This basically represents the power that is converted into the mechanical form. So some portion of the impedance that is representing the losses, that is this one, that is the actual resistance, and the fictitious resistance that is used to just indicate the power that is converted into the mechanical form, right? So R2 into 1 minus S by S represents the mechanical power, is the resistance used for the mechanical power. Okay, then coming towards this branch, this is the magnetization branch and represents the magnetic losses, hysteresis loss, eddy current loss, magnetization loss in your induction machine. In the last lecture, we discussed that the frequency of the rotor is not fixed. Frequency of the rotor is slip times the stator frequency, and because of that, the induced EMF in the rotor circuits keeps on changing. Similarly, if you consider the reactance, which is the function of the frequency, XL is equal to 2 pi f into L. So if the frequency gets changed, the reactance will be changed. So your reactance will be changed and the induced EMF in the rotor circuit will be changed with the change of the speed, right? But we updated the circuit by introducing this virtual resistance over here, such that the EMF can be considered constant over here. This X2 can be considered constant, and all the frequency effect is over here in the resistance R2 into 1 minus S by S, that is representing the energy that is converted into the mechanical form. Okay, now we can simplify this circuit by using basic circuit analysis techniques. So now if I say that for consider the rotor is on this side, and for this rotor, this whole part of your circuit is acting as the source. So this part is going to act as the source one, and the rotor is going to act as the load on this part, because the rotor is extracting the energy from this part. So we can represent this part of the circuit with the Thevenin equivalent circuit, and then we can use the simple analysis techniques to analyze the induction motor in detail. So we are going to now represent this portion with the help of the Thevenin equivalent circuit. So we want the Thevenin equivalent between these 2 points, point A and point B. So we are going to open circuit from this point, and then we are going to represent this circuit with the Thevenin voltage source and the Thevenin impedance, right? So that will be connected between point A and point B. So if I draw it, this is V Thevenin, and then the Thevenin impedance that will be appearing between point A and point B, and then you will be having the rotor circuit, and that rotor circuit will be acting as a load over here. So this Z Thevenin is calculated with the help of this Z1 and this magnetization branch, and V Thevenin is basically the voltage at point A and B when you are going to remove this load. So now let's calculate this V Thevenin. So you are familiar with the Thevenin theorem, so let's apply that one. So in order to determine the Thevenin equivalent voltage source between point A and B, first of all you will have to remove this part, and you will have to look at the voltage between point A and B by using the circuit analysis technique. So over here we can simply apply the voltage division, because you can see that the applied phase voltage will be divided between these two impedance, this part and the this part. Okay, now Over here RC is in parallel with JXM, and RC is usually very high as compared to your JXM. RC is the core resistance, we can say, and represent the eddy current loss. So it should be as small, eddy current loss should be as small as possible, and the eddy current should be as small as possible, and for that RC should be very high. So RC is very large as compared to your GXM, where GXM represents the magnetization of your induction motor. So you know that when a high resistance is in parallel with the small resistance, so its equivalent will be nearly the smaller resistance. So the equivalent of this one will be simply JXM. So first approximation that we are going to make over here, that this RC is quite large as compared to GXM, so we can ignore that one. So using this, I can say that the equivalent circuit will look like this, that R1, JX1, and then we have only the JXM between point A and point B. And over here we are going to apply the phase voltage to our machine. So now we can easily look at the voltage VAB. So that will be the Thevenin voltage, and that can be calculated by simply the voltage division rule. So JXM divided by R1 plus JX1 plus JXM multiply by the phase voltage that you are going to apply. So this will be the Thevenin voltage, right? So Thevenin voltage is simply obtained by the voltage division rule, and in the magnitude form I can write it like that, that V Thevenin is equal to the magnitude of this numerator. So magnitude of the numerator is XM divided by magnitude of the denominator, so that is equal to R1 square plus X1 plus XM whole square, right, into V phase. So in magnitude form you can write down the Thevenin voltage like this. Now what is R1? R1 is the resistance of the copper winding that is used in the stator. So this resistance is usually very small. So R1 is a small number. Usually it is in the range of either milliohms or few ohms. So its square will be even more smaller. So we can neglect this part. So if we neglect this part and consider it equal to 0, then the Thevenin voltage that will be appearing between point A and point B, so that can be written as xm divided by under root of x1 plus xm whole square. So square and square root will be cancelled out, so you will be left with uh, let me write it over here. V Thevenin will be equal to xm over x1 plus xm into V phase. So approximately you can say that V Thevenin is given by this expression. So you need to know about the xm and the stator leakage reactance x1. So if you know that one, you can find out what will be the Thevenin voltage that will be appearing between these 2 points, point A and point B, which are acting as the source point for your rotor circuit. Okay, now after calculating the Thevenin voltage, now we need to calculate the Thevenin impedance. And in order to calculate the Thevenin impedance, what you will have to do, you will have to remove all the voltage sources. So that is obtained by short circuiting this one. So if you short circuit over here, and if you look at the impedance between point A and point B over here, so the impedance will be the Z Thevenin. So that will be obtained by this circuit simplification. And if I draw the circuit, I can write it like that, that R1 and JX1 are now in parallel to your magnetization branch, in which we are going to ignore RC. So we can say this JXM is in parallel with R1 plus JX1, because we need to calculate the impedance between these 2 points, that will be the Thevenin impedance. So between these 2 points your GXM is in parallel with R1 plus GX1. So we can write it like that, that Z Thevenin is equal to R1 plus JX1. This impedance is in parallel with JXM. So solving this, you can find out R Thevenin and the J X Thevenin, and this is the Thevenin reactance, and this one is the Thevenin resistance. So overall it will be the Thevenin impedance. So you can represent this circuit over here now like that, that you have the V Thevenin that we calculated previously, and then we have calculated Z Thevenin, which consists of R Thevenin and the JX Thevenin. So we are going to connect the load over here, and the load is the rotor part. This one, this circuit is going to act as the load, and this circuit is going to be represented with the help of this Thevenin equivalent circuit, right? So the Thevenin equivalent circuit is a very useful to analyze your induction motor circuit. So now let's quickly move towards the slides related to the Thevenin equivalent circuit. So what I was explaining is shown over here. First of all, we are going to measure the Thevenin voltage between these 2 points, point A and point B, and then we will be, when we have calculated the impedance between these 2 points, the Thevenin impedance, right? So if you calculate those ones, so finally you can represent your circuit like this. This was the point A and point B at which you have now calculated the Thevenin equivalent circuit. So Thevenin voltage is over here. Let me show it over here like this. Okay, and this Thevenin voltage, as we calculated earlier, is simply obtained by the voltage division rule. So that was equal to V phase into JXM by R1 plus GX1, and in terms of magnitude it is like that, and we neglected this part. So V Thevenin is approximately given as X M over X1 plus Xm into V phase. So Thevenin voltage is given by this expression, and R Thevenin plus Jx Thevenin, that is the Thevenin impedance, that is given by this expression. So now you can see that the current over here, the stator current, let's suppose I1, that is going to enter into your rotor circuit I2 directly in this circuit, and those can be considered as equal. So now you can easily write down the expression for the power and the torque of your machine. And we have represented over here the rotor like that, Jx2 into R2 by S. We have accommodated the effect of this slip in the rotor resistance R2. Okay, now some approximations over here that I discussed earlier for the simplification of the Thevenin voltage expression. So if you consider that Xm is quite large as compared to X1, and that is the case because this is the magnetization reactance, and this is the leakage reactance of the stator side. So Xm will be quite large as compared to Xm, and Xm will be quite large as compared to R1 as well, because this is the resistance of the copper winding on the stator side, and that should be as small as possible to minimize the copper losses. So I1 square into R1, that's the copper loss in the stator winding. In order to minimize that one, R1 is kept very small, high grade copper is used. So R1 is small as compared to your JXM. Why we are going to consider it smaller than as compared to Xm? Because Xm represents the magnetization loss, and you can say the loss which is there to establish a flux linkage between the stator and the rotor side. So some power is required to establish the magnetic flux in the core of your stator, in the core of your rotor, and to link the flux in between. So it is representing that one. So definitely the whole of the power will have to flow through the air gap when moving from stator to the rotor. So you cannot avoid that loss, magnetization loss Xm, but you can minimize it by controlling the nature and the properties of the material, but still it is quite high as compared to your rotor resistance. So Xm is considered quite high as compared to R1. So with this approximation you can represent your Thevenin voltage with this equation, right? And what about the second expression, this one R1 plus Gx1, that is parallel with Gxm. So that gives you the Z Thevenin. So Z Thevenin is equal to R1 plus Jx1 and its parallel combination with Jxm. So if you simplify this one, so you will get R1 plus Jx1 multiplied with Jxm divided by R1 plus Jx1 plus Jxm. So now you can rationalize this expression and you can separate out the real and the imaginary part. So using this approximation, that Xm is quite high as compared to X1, and then Xm plus X1 will be quite large as compared to R1, when you will rationalize this expression and you will represent it in terms of the real and the imaginary part, so you will see that R Thevenin is given by this expression, that is x R1 into x m over x1 plus xm whole square, and the x Thevenin will be nearly equal to x1. So, x Thevenin is nearly equal to the leakage reactance of your stator side, and R Thevenin is nearly equal to this expression. So, this helps you to give you to calculate R Thevenin and the x Thevenin. Okay. Now, if you have calculated the R Thevenin and the x Thevenin, now you can write down the expression for the current in this circuit. So, this one, if I suppose that the current is I2, I1 and I2 are equal, so I am going to consider it equal to I2. So, if I want to write down the expression for I2, I2 will be simply equal to the Thevenin voltage divided by the total impedance of this loop, right? And what is this total impedance? This total impedance is the sum of R Thevenin plus Jx Thevenin plus Jx2 plus R2 by S, right? So, this is the total impedance. So, with this help, with the help of this expression, you can find out the current in the stator as well as in the rotor side, because this I2 is basically the current flowing through this Jx2 passing through this R2 by S, that is representing the summation of R2 and the resistance that is responsible for the power conversion from electrical to the mechanical form. So, this is equal to R2 by S. So, it can be separated in two parts, and we have seen this dissipation earlier in the slides. Okay, so now the I2 can be calculated. So, I2 is given by this expression. Here you can see the Thevenin divided by the total impedance, and the total impedance is R Thevenin plus R2 by S, right, plus Jx Thevenin plus Jx1. So, that you can observe over here, R Thevenin, X Thevenin, X2 and R2, sorry, this is X2. So, from here I can write that total impedance is R Thevenin plus R2 by S plus J times X Thevenin plus X2, right. So, how to write down in terms of magnitude? So, you will have to take the square of this real part R Thevenin plus R2 by S, that is this one, the real part, and then the square of this imaginary part, that is x Thevenin plus x2, and then the whole square of this one. So, this will give you the total impedance. So, now you have calculated the you can easily calculate the current in the rotor that will be there if you know the R Thevenin and R2 and x Thevenin, x2 and V Thevenin, right. So, in this if I talk about the variable, so what is the variable over here usually for the induction motor? The x2 is fixed, that it is based upon the flux linkage between stator and the rotor, and it is only adjustable at the time of manufacturing. So, it is fixed now, right. Similarly, your x Thevenin, that is equal to x1, that is fixed, and your R Thevenin depends upon if I go back and look over here, xm, x1 and r1, so those parameters are also fixed. So, R Thevenin is fixed. So, this is fixed, this one is fixed, this one is fixed, and the only thing that you can change is the V Thevenin over here. You can control the rotor current by controlling the voltage or by controlling the slip, or in some cases by controlling R2. In the squirrel cage induction motor, this R2 is not controllable, it is fixed. You do not have access to the rotor terminals. However, in the squirrel cage machine, if you use the external resistance with the rotor circuit through the slip rings and the carbon brushes, so then you can control the R2 and you can control the current. But most of the time the squirrel cage machine is used, so this is considered as a fixed terminal. So, only two variables in this equation are the V Thevenin and the slip of your machine. Okay, we have seen in the last lecture that the power that is converted into the mechanical form is given by this expression, that is P converted is equal to 3I2 square into R2 into 1 minus S by S. So, you can visualize it with this expression that I discussed over here, that this resistance is basically the sum of R2 and R2 into 1 minus S by S. So, power that is converted into the mechanical form, that is represented by this part, and how you can determine that power? If you know this current I2, so this power will be I2 square into this converted resistance, power resistance representing the conversion from electrical to the mechanical form. And for 3 phase you will have to multiply it by 3, because this is the per phase equivalent circuit of your induction motor. So that you can see over here that the power is given by this expression 3I2 square into R2 into 1 minus S by S. So now you have calculated the I2, and now you can easily find out the expression for this power that is converted into the mechanical form. Okay, so the induced torque now is given by this expression, that is P converted divided by omega. Mechanical power is represented as like that, torque induced into the omega m. The torque induced is basically the electromagnetic torque that is converted from electrical to the mechanical form, right? So the power that is converted or into the mechanical form will be the product of the torque induced into omega m. So from here we can write down the expression for the torque induced, and omega m is related with the synchronous speed with the help of this expression. Omega m is equal to 1 minus s times the omega s, where this is the synchronous speed of your machine, and that depends upon the number of poles and the frequency. So in terms of rpm, it is 120 f by p, and you can convert it into radian per second. So this is the speed in radian per second. So omega m can be written like this, and this is p converted, and p converted can be written and can be used from this expression. So over here you can see 3I2 square into R2 1 minus S by S. So this 1 minus S will be cancelled by this 1 minus S. So this will be left like that, 3I2 square into R2 by S, this part, right, and divided by omega s, because 1 minus S will be cancelled out. So what is this? This is the power that enters into the air gap of your induction machine. So we can write it P air gap by omega s. So torque induced will be given by this expression, torque induced, that is equal to air gap power divided by omega s. Okay, now the induced torque now can be written in terms of the motor parameters using this equation, because we have already seen the expression for the I2, and that I2 can be utilized over here to find out P converted, and the P converted can be then written in terms of the P air gap, right? So the induced torque will be given by this expression. So how it will be given by this one? Let's write down that equation. So torque induced is equal to air gap power over omega s, and we can write it like that, that P converted is equal to P air gap into 1 minus s. This is the air gap power, this portion. This portion is representing the air gap power, so writing it like that. So I can write it that this P air gap power from here, that will be equal to P converted divided by 1 minus S. So then taking this omega S, that is equal to 1 minus that is equal to omega m divided by 1 minus S. So you can write down the torque induced torque using this equation. Torque induced is equal to P converted by omega m. So just put up the value of I2 in this expression. So let me clear it and show it to you. So from here I can say that power converted is 3I2 square into 3 R2 into 1 minus S by S into I2 square, and I2 is from this expression, V Thevenin divided by R Thevenin plus R2 by S whole square plus X Thevenin plus X2 whole square, right, and the square of this one, and there is the under root as well over here, right. So we can write it like that. We have used the value of the I2 square over here. We are going to use it over here. Okay, so now simplifying this expression, you can write down the power converted expression for the power conversion, and then you can use that expression over here or in this equation to represent the torque induced. Let's suppose I'm going to take it over here. So if I take P converted, and then I write 1 minus S into omega S into P converted, and P converted is 3 into R2 into 1 minus S by S. into V Thevenin square, and because of the square root in will be cancelled out. So we can write it like that, R Thevenin plus R2 by S whole square plus X Thevenin plus X2 whole square, right? So over here 1 minus n and 1 minus s will be cancelled out. So we can simply write from this expression that 3R2 by S into uh, V Thevenin square divided by R Thevenin plus R2 by S whole square plus X Thevenin plus X2 whole square, right? And there is omega S as well. So we can write it like that. And finally, as shown over here in this expression, 3 by omega S from here, and R2 by S, that is this one, and the this portion, right? This is shown over here. So in the Thevenin, using the Thevenin circuit, we have uh, derived an expression for the induced torque, and finally this expression can be written like this, right? 3 into V Thevenin square into R2 by S divided by all of this part, where this is the synchronous speed of your machine, and all of these are the machine parameters. So we have expressed the torque induced in terms of the machine parameter, equivalent circuit parameter, R2, X Thevenin, X2, X1. So it is in terms of machine parameters. Externally, we are going to apply this voltage, so we can control the voltage with the help of the we can control the torque with the help of the voltage, and we can control the torque that is induced with the help of the slip as well. Slip is an important parameter over here, because that depends upon the speed. With the variation of the speed, slip will be changing and induced torque will be changing. So if we sketch this torque speed curve, keeping all the parameters constant, only we keep the slip as a variable, and slip, as you know, that is based upon the stator and the rotor speed, ns minus nr divided by ns, that gives you the slip speed, or simply the slip. This is the slip speed, and s minus nr, and divided by ns will give you the slip. Okay, so if you sketch that torque speed curve, so that will be somewhat like this. In this, we have considered all the machine parameters constant. V Thevenin is constant. We are only varying the speed, right? And the speed may be changed in the number of ways. So you can see the sketch of the torque speed curve. At the start, your machine is going to provide a reasonably higher torque, that is said to be the starting torque of your machine. And once your speed is increasing, so slip is decreasing, and the maximum torque that can be delivered by your machine is called the pull-out torque, and that is this one. And then if you are further increasing the speed approaching to the synchronous one, then you are in this region of the torque speed curve. We have already seen that this slip of your machine is very small, usually is 1 to 10% only. So your machine will be operating in this region of the torque speed curve, and that is the linear region. So we usually operate our induction motor in the linear region of the torque speed curves, right? So the starting torque of your machine should be higher than your load torque. This is the load torque. If your starting torque is higher, then your machine can easily accelerate. But if your starting torque is somewhat like that, if your torque speed curve is like that, and your load torque is higher than the starting torque, then your machine will not be able to start, because you can see this is the load torque, and starting torque. This is the T start, starting torque of your machine, and this is the load torque. So if the load torque is constant and your starting torque is smaller than that one, your machine will not be able to start. So to the start of your machine, your starting torque should be higher than the load torque, right? And this is the point of equilibrium, because when your machine is accelerating, so at this point the torque developed or induced is higher than the load torque, and similarly over here it is increasing, machine is accelerating. So as the speed is increasing, the machine parameters are such that more and more torque is being introduced. So machine is accelerating, reaching over here, and then because of the machine parameters, the torque will be reducing like that. and finally the machine is accelerating to this point, and over here the load torque and the machine torque becomes equal. I am considering this one as the load torque. So this is the point of equilibrium at which your machine will be operating, because at this point your load torque is equal to your machine torque, that is the induced torque of your induction motor. So this is the point of equilibrium at which your system will be operating, right? So if you change the voltage of your machine, the Thevenin voltage, so what will be the impact over this torque speed curve? If you go back and look at this expression, let me clear this part. So from here you can see the torque induced is directly proportional to the square of the voltage. So if I keep all of these parameters constant and we only change the slip, so we get this torque speed sketch that discussed over here, that is basically obtained by plotting induced torque with the slip versus slip. Okay, so slip basically change by changing the speed. So over here you can see the speed, mechanical speed. So mechanical speed is increasing over here, and if I talk in terms of the slip is decreasing. Slip is 1 over here and the 0 at the synchronous speed. So slip is decreasing from 1 towards 0, but your mechanical speed is increasing from 0 towards your synchronous speed. Okay, now if I look at the effect of the voltage, so voltage as we have seen, the torque induced is proportional to the square of the Thevenin voltage. So if you increase the voltage, so the torque will increase by the square. So with the increase of the voltage, the new torque speed curve will be like that, and if you decrease voltage, the new torque speed curve will be like this, right? So the torque induced will be decreasing if you decrease the voltage, and will be increasing if you increase the voltage. So with the variation of the voltage, Thevenin voltage, that you can control with the help of the variable supply at the machine terminal, or you can control with the help of the inverter in the case of the drives. So when you will be changing the voltage, the torque speed curve of your machine will be changing like that. So now let's suppose that I have the load torque, that is like this. This is representing the load torque, and I want to operate my machine, let's suppose, at this particular speed, right? This is the requirement. So I should adjust my torque speed curves in such a way that there is the point of equilibrium at this point. Why selecting this point? Because this is the low torque and we require this speed. So at this speed your motor torque should be equal to the low torque. If that is the case, then your machine will be operating at this point. So how you can do this one? You can change the voltage so that you can adjust your torque speed curves. One way of that one. So let's, for the timing, I'm going to change this point. Let's suppose that this is the point. This is the speed at which we want to operate our machine. So if you adjust the voltage, you can run your load at this particular speed, let me call it N1, and you will be fulfilling the low torque demand. So you can change the voltage if you are using this curve, right? So point of intersection is this one, so your load will, there is no intersection over here, sorry. So point of intersection is this one, so it is at different speed. So now you want to run your load at this speed, so you are going to reduce the voltage such that the torque speed curves becomes like this, and the point of equilibrium is this one, right? And if you further reduce, then the point of there is no point of intersection for this torque speed curve, so load torque is quite high, your machine will not be able to run this load. And if you look at this torque speed curve, so it is intersecting this load curve at this point, and that is, let's suppose N2. So you will have to adjust the torque speed curve by controlling the voltage that where you want to establish the point of equilibrium. And how you adjust this voltage now, this is done with the help of the inverter in the case of the drives. With the help of the inverter, you have seen the lectures, in the previous lectures we have discussed about the space vector PWM that is used to control the inverter output voltage. So with that you can adjust this torque speed curve up and down, and you can control the point of equilibrium, and you can adjust the point of equilibrium according to your requirement. Okay, now let's look at the other thing, one other important thing, and that is the frequency. Where is the frequency in this expression, the torque induced expression? So if I directly look at that one, you cannot see the frequency, but that is hidden over here because this omega s, the synchronous speed in terms of rpm, it is 120 f by p. It is the function of frequency. By changing the frequency, your synchronous speed will be changed. So it means you can change this point, synchronous speed point, if you change the frequency. And what is its relationship with the torque? If I expand that one, if I say this omega s is equal to 2 pi f, if I relate it with the hertz, so torque induced is inversely proportional to the frequency, right? So torque induced is inversely proportional to the frequency from here, because frequency is hidden over here in the expression of the synchronous speed. So if you increase frequency, the induced torque will be reduced. And how your torque speed curves will look like in the case of the change of frequency? Let's suppose I am going to increase frequency. So if I increase frequency, induced torque will decrease. So new torque speed curve will be like this. And I am assuming that I am only changing the frequency. All other parameters are constant. Voltage is constant, machine parameters are constant. So with that, your torque speed curve will change like this, and this is your new synchronous speed. But the magnitude of the torque that you can get will be reduced at all the points. And if you further increase the frequency, so your torque speed curve will become like this, and so on. If you keep on increasing the frequency, you can operate your machine at the higher speeds but at the reduced torque. Let's suppose that my load torque is this one, a constant load torque. So now I can operate it at number of points. I can operate it over here or not at this point. So I can not operate it over here because the load torque is higher than your starting torque. First of all, your machine is not going to start. The equilibrium points are over here in the 1 to 10% slip range. So you can operate your machine at either of these points. So what you will have to do, you will have to select the torque speed curve up appropriately. But now if I say that I am going to operate my machine at this speed, let's suppose this is N2, and definitely we can operate it at, but this is the torque speed curve for this particular point. But now look at this one. What about the starting torque? The starting torque is less than the load torque. So your machine cannot start your load with these torque speed characteristics. Means if you are operating your machine with this frequency, you cannot start. So what you will have to do, you will have to keep your frequency lower at the start. Let's suppose that you select the frequency of this curve, frequency f1. So starting torque will be quite high as compared to your low torque. This is your low torque. So starting torque will be high and your machine will accelerate. But once your machine start accelerating, it is gaining the speed is increasing. So when you are entering into this region over here, what you can do, you can now control the frequency and you can change the frequency so that this curve is followed, second curve, right? So if that curve is followed, you can operate your machine at this point. But and if you change the frequency to the frequency of this curve, you can operate your machine at this point. And if you change the frequency to this curve frequency, so you can operate your machine at this point. However, its starting torque is not sufficient for this curve. If I particularly consider this curve, starting torque is not sufficient, so we have started our machine using this torque speed curve because starting torque over here was quite high. But once the machine starts, we change the frequency in such a way that from this torque speed curve we are going to shift to this torque speed curve so that we can operate our machine at this point of equilibrium, which is the desired speed for this particular load. But we can run only this load. So you can switch between the torque speed curves, and you can decide about your equilibrium point, and you can operate your machine at that one. So with the frequency variation, you can see over here the torque magnitude of the torque is going to reduce. You can run your machine at the higher speeds, but you will have to compromise over the torque. So if you say that the torque demand is this one, Of course, you can change the torque speed curves uh, to, if I'm only going to use the voltage, let's suppose. So only with the voltage, the torque speed curve variation will be like this, right? Only up and down movement will be there with the voltage. You can move your torque speed up, or you can move your torque speed curve down by changing the voltage. And if you change the frequency, you can shift your torque speed curves left and right. So this left right adjustment will be with the help of the frequency, and up down adjustment will be with the help of the Thevenin voltage, right? So now you have two control parameters, the voltage and the frequency, and you can adjust your equilibrium point anywhere over this plane within certain boundary limits that depicts demonstrate that how much maximum torque can be produced by your machine, and how much maximum frequency may be there at which you can operate your machine. So within those boundary limits, because on this axis you can say you have the limit of the frequency, because when you are going to change the frequency, you can change the synchronous speed. Torque speed curve may be like this. For another voltage and frequency combination, it may be like this. So for different voltage and frequency combination, you can have different torque speed curve. So we can say this is the upper limit of the voltage, right? And our torque must not go beyond that one, and this is the upper limit of the frequency f max, and we have V max over here. So we will be controlling the voltage and the frequency in such a way that our torque speed curve are there in this region, and the point of intersection is our desired point that we want to run our machine, let's suppose at this speed with this particular torque. So we can adjust the voltage and we can adjust the frequency with the help of the inverter to adjust the equilibrium point. So you have seen the inverters in the previous lecture. Inverters are basically the circuits which takes the DC supply and convert it into AC as per your requirement, as per your required voltage and the frequency, and this is the control port of that one. So this circuit basically consists of the IGBTs, of the MOSFETs, the semiconductor devices which are controlled with the help of the microcontroller and the processor. By these two are going to generate the gate signals for your MOSFETs, for your IGBTs, and those are turned on and off such that you get the required voltage and the frequency at the machine terminal, so that you get a certain torque speed curve, because torque speed curve is the most important one in the drives, because with the help of the inverter you adjust the voltage, you adjust the frequency, and the torque speed curve is changing, and basically you are tracking the point at which you want to operate your machine. If you want to operate your machine at this point, you will have to carefully look that either your machine can start this load or not. If you are operating your machine with this frequency, you cannot start with this frequency, you cannot start, you can start with this frequency, and here is the point of equilibrium. But if you want to operate at this speed, right, so then what you will have to do, you may start at some other torque speed curve, and then adjusting the voltage and the frequency, you can establish this point of equilibrium, right? And if I talk about this one, definitely if you look at this torque speed curve, you cannot start. But first of all, what you will be doing, you will be starting at the with the help of this curve, and once your machine is started, you will adjust the voltage and frequency such that the equilibrium point is this one, that is the new torque speed curve is this one. So starting with this torque speed curve and switching to this torque speed curve will help you to run your machine at this speed, fulfilling the load torque demand. Similarly, if I want to operate my machine at, let's suppose, at this point, so I need this torque speed curve, right? But let's suppose that this is the load torque, right? But what about the starting torque? Starting torque is smaller than the load torque, so this torque speed curve cannot start our machine. So what we will have to do, we will have to go for this torque speed curve, because its starting torque is higher than the load torque. This is the load torque line, right? So starting torque is higher, this torque speed curve can start, but once your machine is started, from this torque speed curve you will jump to this torque speed curve, and then you can operate your machine at this equilibrium point. So it's the game of voltage and the frequency, that how you can control the voltage and the frequency within certain boundary limits, so that you can operate your load at the desired speed, or you can fulfill the load torque demand with the help of the induction motor, right? So the torque speed curves plays a very important role in the design of the drives. You must have the torque speed characteristics of your induction motor so that you can decide at what flexibility of the voltage you have, what frequency of the frequency variation you have, and then you can control your inverter to set the point of equilibrium so that you can stably operate your system. So that is the basics of the drives, and for that you must have the equivalent circuit, and we have seen in the previous lecture and in today's lecture that how we can simplify the equivalent circuit of the induction motor such that we can develop the torque speed curves. So you must know the machine parameters. Okay, so we have seen the effect of the voltage. With the voltage, the torque is directly proportional, right? And rather, the torque, induced torque is directly proportional to the square of the Thevenin voltage, and the induced torque is inversely proportional to frequency, and the induced torque is linked non-linearly with the slip as well, and this shape of the curve, torque speed curve, is in front of you that relates the torque and the speed, slip or the speed. So torque depends upon this one. Torque also depends upon the machine parameters R2 and X2, X Thevenin, R Thevenin. But over here, if you have the squirrel cage machine, you cannot change any of this parameter, neither X2, neither X Thevenin or the X R2. So you cannot control these ones. However, if you have the wound rotor type machine, then you can use these this R2 to control the torque speed curves. But nowadays it is not used. We have the voltage and the frequency control with the help of the inverter, and we adjust the torque speed curve. To adjust the resistance, definitely you will have to connect the mechanical resistance coupled with the rotor circuit through the slip rings and through the carbon brushes. That will increase the mechanical size, that will increase the losses because of the current in this external resistance that is connected to the rotor circuit. So this method is not used nowadays. This was not an efficient method. Nowadays we are going to use only the frequency and the voltage control and the frequency control to control the torque speed curve. But we will look at the effect of the resistance or rotor resistance over the torque speed curve. Okay, so now let's quickly go and look at the effect of the rotor resistance. So in order to look at the effect of the rotor resistance, first of all I am going back to the equivalent circuit over here, and I want to explain you one thing, that where this power is being utilized. If I talk about this diagram over here, so from here the power is entering into the air gap, right? From this point, from here, this is the air gap and the power is entering into the rotor. On this side we have the stator, this side we have the rotor, in between we have the air gap power. So where this air gap power will be utilized? This is basic, because reactance is not utilizing this power. The power utilization is over here at R2 by S, and this has two parts. We have previously discussed R2 and R2 into 1 minus S over S. This is, you can say, R converted, representing the power that is converted into the mechanical form. So the power that is entering into the rotor circuit is utilized over here at R2 by S. Some power is lost as a rotor copper loss, that is across R2, and the rest is converted into the mechanical form, that is represented by this resistance. So these two resistances are utilizing that power that is entering from air gap into the rotor circuit. Now you are also familiar with the maximum power theorem, that when the source impedance becomes equal to the load impedance, so you can extract the maximum power from your source. So if you are looking at this point, point A and B, so when the rotor circuit will be extracting the maximum power, when the impedance of this side will become the impedance of your source side, and looking from point A and B, this must become equal to the impedance that is shown by your this Thevenin impedance. Right. So if I am looking at from these 2 points, so from here, if this impedance becomes equal to this one, you can extract the maximum power at these 2 points from this circuit which is acting as the source for your rotor, right? So in order to extract the maximum power, you should have the same rotor impedance as that over the R Thevenin and JX Thevenin. If that is the case, you can extract the maximum power. If you are extracting the maximum power, you know that this power that is converted into the mechanical form. If you are going to maximize that one, so your torque induced that is equal to P by omega, right? So P is equal to P omega, sorry, P is equal to T omega. From there I have written this one. So what about your torque? If your power becomes maximum, your torque also becomes maximum. So you can get the maximum torque by maximizing the power, right? If you maximize this power, so you can get the maximum torque. And to maximize this power, you can take the advantage of the maximum power theorem, that your stator resistance and the rotor resistance, or you can say the impedance over here should become equal to the impedance on the source side, because the boundary line is this one, A and B. This is acting as the source, this is acting as the load. So load impedance becomes equal to source impedance. You can get the maximum power, and if you have the maximum power, you have the maximum torque. So you can extract maximum from your machine. Okay, so now using this concept in mind, the maximum torque occurs when the power transferred to R2 by S is maximum, right? We have just seen it in the equivalent circuit. So if I draw the equivalent circuit over here, just to look at this expression in detail, so we have this one, R Thevenin, Jx Thevenin, right, and then we have Jx2, and we have R2 by S, and this is the Thevenin equivalent circuit. And let's consider for a time being that this is the load. This R2 by S is going to act as the load, and when the maximum power will be extracted by this R2 by S, when this R2 by S will become equal to this part. So I can say that R2 by S should be equal to R Thevenin square plus X Thevenin plus X2 whole square, the magnitude of this impedance, right? So what will be this S? If this condition is there, that R2 by S is equal to this part, it means your power is maximum, and if your power is maximum, it means your torque is maximum. So this is the slip corresponding to the maximum torque. So we are going to write T max with that one, that you can see over here. This is not the maximum slip, this is the slip corresponding to the maximum torque, and where it will be there in your torque speed curve. If I go back and look at the torque speed curve over here, so where is the maximum torque? The maximum torque is this one, that is said to be the pull out torque. So the slip corresponding to that one, this is ST max, slip corresponding to the maximum torque. And when you are going to change frequency, this is going to change because your torque speed curve is changed. This is your new torque speed curve. If you increase, so your this speed or this slip at which your maximum torque is going to occur, that is going to change. So maximum power will be delivered when R2 by S will be equivalent to this impedance, and using this expression we are defining a condition for the slip corresponding to the maximum torque, and with this expression now you can calculate that slip, at which slip your torque will be maximum, that is given by this expression ST max, that is equal to R2 over R Thevenin square plus X Thevenin plus X2 whole square, and then the under root. So this is the slip corresponding to the maximum torque, or when the maximum power will be delivered, right? So now we can write down an expression for the maximum torque. How? Just go back and look at the torque speed expression that we derived. This is the torque speed expression we have derived, right? So now in this we are going, if we keep all parameters constant, the voltage constant, omega is constant, R Thevenin constant, X Thevenin, X2, and R2. If I replace this slip with this slip corresponding to the maximum torque, not the maximum slip will be 1, because slip is varying from 0 to 1, but this is the slip corresponding to the maximum torque. So what will be this induced torque? This will be the maximum one. So now we are going to replace that expression of the maximum torque slip in this expression, let me call it A, and we are going to simplify. So after simplification you are going to get this expression. You should be able to do that simplification at your end. So this is the expression for the maximum torque that will be delivered. So here you can see that it depends upon the Thevenin voltage, and this is the per phase equivalent circuits of phase voltage, and that you are going to adjust from your inverter in the case of drive. And it depends upon R Thevenin, it depends upon X Thevenin, it depends upon X2, and it depends upon frequency as well. Where is R2 in this? The R2 is eliminated. Your maximum torque does not depend upon R2. Right? So the slip at maximum torque, the slip at the maximum torque depends upon R2, that you can see over here. If you change R2, you can change this slip. If I want to look at the effect of the resistance over the torque speed curve, rotor resistance, so from that can be depicted from here, that ST max is directly proportional to the R2. If you increase rotor resistance, you can change that slip. And what that means, that if I go and look at this torque speed curve, let me remove this previous writing. So this is the torque speed curve, and now if I change R2, what will happen? Are we changing frequency? No, synchronous speed will remain same. We are not changing the voltage at all. We are just only changing the rotor resistance. How? And that is only possible in the case of wound rotor type machine. So if I change the rotor resistance, what will happen? The new torque speed curve will be like this, because we know that ST max is equal to R2 divided by, what was that equation? R Thevenin square plus X Thevenin plus X2 square. So R Thevenin square plus X Thevenin plus X2 whole square, and all of this is in the under root, right? So if we change R2, it is directly proportional to that one, and if we increase R2, slip will increase. Increase of slip means we are moving the maximum torque point towards left. So if we change this one, this will be new speed, ST max new. Previously, let's suppose that it was operating over here, slip T max 1. It was giving you the maximum torque at this point, at this slip. But if you change R2, now you will be getting the maximum torque at this point, at lesser speed, because slip is increased. Increase of slip means the speed is reduced. And if you further keep on increasing R2, you can bring this point like that, and your torque speed curves will look like this. And by further increasing, you can show it like this. So what is happening now? With the increase of R2, the point of the maximum torque is moving towards your left. So if you have, let's suppose this torque speed curve, let me mark it over here. This is the low torque that we require, and I have this torque speed curve. I cannot start, because my starting torque is lesser than the low torque. If I increase R2, new torque speed is this one, starting torque is increased, but still not sufficient. If I further increase R2, starting torque is increased, but not sufficient. Now further increase R2, starting torque is higher than the low torque. Your machine will start. And this is the point of equilibrium at which it can be operated. This is the point of equilibrium. So your machine will be operating at this speed. But what if I do not want to operate my machine at this speed? Once our machine is started with the higher value of the R2, because no maximum torque, starting torque is increased and the position of the maximum torque is changed, and then I can reduce the resistance. So I will be jumping from this torque speed curve to this one, and this will be the point of equilibrium. Our machine will be operating at this speed. And if I jump to this torque speed curve by changing the R2, I can operate my machine at this point. So we can control the point of operation with the help of the rotor resistance as well. But this is not used nowadays. Why? Because we will have to mechanical assembly on the rotor side, and we will be having the losses in that resistance that we will be inserting in the rotor circuit. So inverter based control is used, voltage and frequency control is used, but R2 can also be used. You will find it in the previous applications, decade back applications, right? So with the change of the R2, you can see the slip corresponding to the maximum torque is changing. And what about the peak effect? Effect over the T max? It is not changing. Why? Because we have seen the expression. If I go back and look at that expression for the maximum torque, is it depends upon R2? No, it does not depends upon R2. So by changing the rotor resistance, the point at which this maximum torque is going to occur, that is changing. The position of the maximum torque is changing, but the magnitude of the maximum torque is not changing. So the slip at the maximum torque is directly proportional to the rotor resistance R2. But maximum torque is independent of R2. Right? So maximum torque is independent of R2. R2 is not going to change the maximum torque. That you can see over here. It is fixed. Maximum torque is fixed. It is not changing. But the position of that maximum charge, the slip corresponding to that one, that is changing. That you can see over here. Slip for this value of R2, this value of R2 and so on. So if I say this R2, let me call it R2 prime. So this will be greater than this R2. And R2 double prime, that will be greater than the previous value. So if you keep on increasing the value of the R2, so your torque speed curve's peak value will be shifting towards your left. Peak value is shifting, will be changing its value, but will remain constant. Because Tmax is independent of R2. It does not depend upon R2. The position of the maximum torque depends upon R2. Right? So you can control your torque speed curve with the help of the rotor resistance. If this is required, you can use that one. If you do not want to use the inverter, you can get this stuff done. Okay, so now finally I want to discuss the voltage and the frequency effect. With the voltage, the torque speed curves are going to change like that. Synchronous speed is not going to change because synchronous speed is only the function of the frequency. So with the torque, you can change your torque speed curves like this. You can move them up and down. Up down movement with the help of the voltage. Definitely you cannot go above the rated voltage. You can have the damage of the insulation. Insulation depends upon the voltage that you are going to apply. So winding insulation may be affected if you operate it at higher voltages. So it is not recommended. So this voltage variation is between 0 and the Thevenin maximum rated voltage per phase. And if now I talk about the frequency, with the frequency we can change the torque speed curves like this, left and right. But with the increase of frequency, the magnitude of the torque speed curve will be decreasing. And for lower frequencies, we can have higher magnitude as well. So, this is my reference point, reference curve. So with respect to this reference, if I increase the frequency, torque speed curve will be moving towards your right, and if I decrease the frequency, torque speed curves will be moving towards your left, and the magnitude of the maximum torque will be increasing. But again, definitely there is a mechanical limit as well, at how much maximum torque can be sustained by your shaft. Now if I control voltage and frequency both, such that we can keep this torque speed curve at the constant level. For example, I am reducing the frequency, but at the same time if I reduce voltage, so what will be our new torque speed curve? Let me draw it over here. I can have this one by selecting a pair of the voltage and the frequency. So V by F control the ratio of the voltage and the frequency, right? So you can get this peak with the new torque speed curve, keeping this constant. You can have a combination of the voltage and the frequency. You can change voltage, you can change frequency, and you can have this curve. Now if I want this curve, I can have a combination of voltage and frequency. And to have this curve, I can have the combination of the voltage and frequency. So you can change the voltage and frequency in a proportional. So if I summarize, you can control voltage. By controlling the voltage, you can move up and down. By controlling the frequency, you can move left and right. By controlling the R2, you can change the position of the maximum torque, but you cannot change maximum torque. And if you control both voltage and frequency, you can adjust your torque speed curve in a certain given region. Let's suppose this is that way. So you can adjust, you can keep your peak constant, and you can have a different synchronous speed. So torque speed curve is the most important thing in the drives, and the information of the load torque is very important, because with respect to that one you decide at what frequency, at which speed you need to run your load, then you decide about voltage and the frequency, and that is realized by your inverter circuit. Inverter adjusts the voltage and the frequency at the machine terminals. So drives plays a very important role in the control of your induction motors, and for that you had the deep understanding, thorough understanding of the torque speed curves and the factors on which it is going to depend. You can control them by machine parameters, by voltage, frequency, anything can be changed. And we have different classifications of the motors based upon these shape of the torque speed curves. I'm not supposed to go into detail of that one. I just want to discuss it from control point of view, and how we can control the torque speed curves with the inverter to control our induction motor drive. By controlling this slip, we can run our motor as a generator as well. If we have some external mechanical source coupled with the shaft of our induction motor, and if we change the speed of that slip is going to become negative, then the power will become negative. Negative power means it is going to flow back from your shaft towards your electrical source. It means it is working as a generator. Anyhow, we are not discussing it in detail. Our main purpose is to understand the induction motor drives. Okay, so with the increase of the resistance, as I have already explained you can see over here how the torque speed curves are going to change. If you keep on increasing the rotor resistance, these are going to change like that. The maximum torque is constant, its position is going to change, and that can be done with the help of the V by F control as well, as I told you. Okay, so next there is an example. So now I will share this slide so you can go through that example at your end. So if I summarize this lecture, we have discussed the torque speed curve for the induction motor in detail from drive's point of view, and we have seen that how voltage, frequency and the different machine parameters affect the torque speed curve. That's all from this lecture. Thank you very much.